Let's pretend there's a flight scheduled on a plane with 50 seats, and let's pretend the flight is sold out, so all 50 seats have a paying passenger in them. And let's suppose all passengers have an assigned seat, so passenger 1 is assigned to seat 1, passenger 2 is assigned to seat 2, and so on and so forth. And let's pretend the airline forgets or loses track of everyone's seat assignments and tells all of the passengers to sit in a random seat once they board on the plane. What is the probability that no passenger sits in their originally assigned seat? Or in other words, what's the probability that everybody ends up in the wrong seat? The true answer involves some combinatorics to figure out, but in this video, we're going to use the power of simulations and numpy to estimate the answer with very high accuracy. Let's think about how we might go about doing that. Here I've produced an array with 5 numbers, 1, 2, 3, 4, and 5, and you can imagine this represents passenger 1 sitting in seat 1, passenger 2 sitting in seat 2, passenger 3 sitting in seat 3, and so on and so forth. So pretend this is what the plane would look like if everyone actually sat in their correctly assigned seat. To imagine what the plane would look like when everyone goes and sits in a random seat, we can use the power of np.random.permutation, which will take this seats array and shuffle it up. Note that every time I run this cell, it gives me back a new ordering of the numbers 1, 2, 3, 4, and 5, and I can interpret this resulting array as being one simulation, if you will, of everyone boarding the plane and sitting in a random seat. In the simulation that we're looking at on the screen, this is saying that passenger 2 sat in seat 1, passenger 1 sat in seat 2, passenger 5 sat in seat 3, passenger 3 sat in seat 4, and passenger 4 sat in seat 5. So in this simulation, all 5 passengers sat in the wrong seat. If I run it again, here we see that passenger 3 does indeed sit in their correctly assigned seat. And so the nice thing with numpy expressions is that I can run them as many times as I want, perhaps in a for loop or something like that, and each run gives me another simulation of this process of people boarding the plane and sitting in some random seat. In some of those simulations, like the one on the screen right now, some people do sit in the correct seat, like person 2 sits in the correct seat, and in other simulations, like the one that's on the screen now, everyone sits in the wrong seat. Here's where probability comes into play. I can estimate the probability that everyone ends up in the wrong seat by just simulating this shuffle many, many, many times, say 100,000 or 1,000,000 times, and count the fraction of simulations in which everyone ends up in the wrong seat. So in other words, I could run this cell 1,000,000 times and then estimate the probability that everyone is in the wrong seat as being the number of times everyone was in the wrong seat in a simulation over 1,000,000. And probability theory tells us as long as we run a large number of simulations, this estimated probability by taking the number of successes over the number of total simulations will converge on the true theoretical probability with high certainty. So that's what we will try here. We need some way to repeatedly run np.random.permutation to get a new shuffling of everyone on the plane and then keep track of whether or not everyone was in the wrong seat. Here's one way I might do that. What I've done here is I have shuffled to a particular permutation, and every time I run this cell, it's going to give me back a new shuffling, which I'm printing out here. And what I've done is I've compared the shuffled array to the original seats array, which is 1, 2, 3, 4, and 5, and I've taken the sum of that array. First, what is that array without taking the sum? It's an array of trues and falses. There's a true in each position if that seat is filled by the person that's assigned to it, and there's a false if someone else is sitting in that seat. So in this example, I have false, 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 because everyone is in the wrong seat, right? This isn't person 1. This isn't person 2. This isn't person 3. When I run it again, I get another false. When I run it again, I get another false. But in this case, lots of people are actually sitting in their correctly assigned seats. I have a true here because person 1 is in seat 1. I have a true here because person 2 is in seat 2. And I have a true here because person 4 is in seat 4. So to check whether everyone is in the wrong seat, it just boils down to checking whether the sum of this array is 0. If it's 0, that means everyone's in the wrong seat. But if it's anything above 0, well then there had to be at least one true in this array, which meant that at least one person was sitting in the right seat. So this boils down to running this cell lots and lots and lots of times and counting the number of times I see a true. Because anytime I see a true, it means everyone was in the wrong seat. So instead of manually running this cell repeatedly myself, it's perhaps a good idea to define a function that runs this cell once and then maybe call that function within a for loop. Let's try that. I'm going to define a function called everyone in wrong seat. And instead of deciding in advance how many people are going to be on my hypothetical plane, I will let this be an input to my function. So I'll say seats is np.arange not 1 to 6, which would be 1, 2, 3, 4, 5, as in the previous example. I'll let it be np.arange 1 to n plus 1. And as we will soon see, as you increase the value of n from 50 to 100 to 1,000 to 10,000, the resulting probability doesn't actually change very much because it converges on a particular value for a relatively small n, and then it stays around that value for any n, essentially. Okay, but otherwise I'm going to keep the same setup. I'm going to have my seats, shuffle them up, and count how many people ended up in their originally assigned seat. And I'll say flag equals this value. This value is either a single true or a single false. Okay? And essentially, if this flag is true, in other words, if it's the case that nobody ended up in their correctly assigned seat, well then I'm going to return true, and otherwise I'm going to return false. But it turns out I don't need this if-else block. I can just return flag. And I also don't really need to assign flag to its own variable. I could just return the result of this check. Okay, so this will function perfectly. And now every time I call it, so let's pick our n to be, say, 50 people on this hypothetical plane, it's going to simulate one hypothetical plane. Okay, it's going to pick 50 people, shuffle them up, and return true if everyone was in the wrong seat, and false if at least one person was in the correct seat. Okay, if it says false, we don't really know what the makeup of the plane is. Other than that, at least one person is in the right place. If it says true, though, it means everyone is in the wrong seat. So now what this boils down to is running this cell repeatedly, and counting the number of times we get a true. Okay, and so maybe I'll set this up like this. I'll assign count to initially be 0. And for I in range, let's just say 100,000, I'm going to say my flag is the result of calling everyone in wrong seat 50. And I'll say if this flag returned true, I'm going to add 1 to count. And I do that in Python by writing count plus equals 1. Otherwise, I'm not going to do anything. And now let's just look at what count ends up being. Count ends up being 36,713. And so that's our numerator here, the number of simulations where everyone ended up in the wrong seat. My estimate of the probability that we're looking for is that numerator divided by the total number of simulations. And so here that's 0.36713. So that's saying our estimate of the probability that if everyone ends up in the wrong seat, if our plane seats 50 people, is 36.7-ish%. Check it out. If I change our hypothetical plane from seating 50 people to 500 people, so now there's seat 1, seat 2, seat 3, all the way through seat 500, the estimated probability doesn't change very much. It's still in the neighborhood of 36.7-ish%. And it turns out we can prove that the answer approaches 1 over e, that mathematical constant you learned about in calculus, like 2.718 and some change. This is the probability that, for a sufficiently large n, everyone ends up in the wrong seat. Now, why it's 1 over e, we're not going to have time to prove that in this video, but that's the kind of thing I'd happily walk you through in office hours, and it involves some nice permutations and combinations and principle of inclusion-exclusion logic you may have seen in previous courses. So, to answer the initial question, what's the probability everyone ends up in the wrong seat? It's about 1 over e. And this is just one of the many applications of real-world problems that seem like they have nothing to do with calculus, that have an answer that involves that mathematical constant, e. Thanks for watching.